Alrighty, like I said, I know we're gonna go through, I better find the right tab. I know we're gonna go through this week with the global warming / greenhouse gas thing. Tomorrow is short, like yesterday, on pollution. Today is the long one. Today is about ministry. We will review Thursday. I made the paper review, but I haven't done the Kahoot version yet. The test is Friday, unless something weird happens, like my kid tries to catch my house on fire again. Yeah, I had a hard time sleeping. My whole house just reeks of smoke. Which, can't stand the smell of smoke. Next week, I know I won't be here Monday. I'm not quite sure what the heck I'm going to leave for you. I don't know what we're doing next week. I'm going to have like 3 days worth of something. Still want to give you a day to be able to do your notebooks, get those in their test grade, and then that next week, it's right around the corner. That next week is 6 weeks test, CDAs. So, which is, I get to make your CDA, so it won't be weird. For the opener, you should know at least one of them. There's 4 major greenhouse gases. Which would they be? Not in their natural state, actually, no. Carbon dioxide's one. Water vapor's another. Methane's another. You gotta let me know, unless you're reading off on the paper or on the thing. It's nitrous oxide. It's N2O. Nitrogen gas and oxygen gas in their normal state are not greenhouse gases at all. And if we didn't have photosynthetic plants, oxygen wouldn't stay in the atmosphere. And if we didn't have the magnetosphere, the solar radiation would strip the gases off this planet the way that basically happens to Mars.
Did you say nitrous?
Nitrous, yes, nitrous oxide. There's nitrous and there's nitric or nitric, same thing. Just depends on, potato. I've never heard somebody call a potato a potato. I, believe it or not, as we go through this, I have condensed this as much as possible. If you see GH, that stands for greenhouse, GHG, greenhouse gases. Because otherwise, if you're trying to type it out over and over and over and over, you're gonna run out of time. But we thankfully have a mild greenhouse effect on this planet. Okay? Venus's greenhouse gas is nuts. Okay? It's hot enough to melt lead on the surface of Venus because of its greenhouse effect. Now, obviously, it's closer to the sun anyways. But yeah, it's hot enough to melt lead on the surface of Venus. It's been a while since we've done space. Mars has a thin atmosphere. Okay, so it has a minute greenhouse effect. So what the greenhouse effect does is it allows infrared heat to be trapped by the atmosphere to keep the surface, wherever the atmosphere is, warmer than it would be if there was no protective blanket that we call an atmosphere. Ours is like Goldilocks, like it's perfect. It's not too hot and it's not too cold. And yes, I know we have fluctuations, and we've been talking about what happens to our atmosphere for a while now. But in general, I'm not sure what 34 degrees Celsius translates to Fahrenheit. Well, here, I'm gonna cheat. Yeah, it's something like that. I know there's a conversion factor, but let's see, 34 Celsius to Fahrenheit. 93 degrees. Okay, so if we did not have this greenhouse effect, you can take 90 degrees off the top, and that's how cold it would be, planet-wise. Okay. Sorry, inhaling that smoke has gotten me. So like I said, Venus is much warmer. Yeah, it's closer to the sun. It has a very, very thick atmosphere, much warmer than it should be if it did not have its greenhouse effect. Mars does have an atmosphere. It's thin. The warmest that Mars does get is about the temperature here. Ew. I still can't believe they have rat electrocuted in the room. That has to smell so bad. But like I said, we've got Visible light, we've got a lot of things coming from the sun. We've got radio waves, we've got microwaves, and we don't have the gamma and the X-rays, and like the most of the UV is stopped by our ozone layer. But the visible and the infrared that makes it through gets basically reflected off the surface and then trapped by the gases, and it keeps our atmosphere warmer. That's how they work. And so this is actually mentioned on the next slide. I should have taken that one off. It's just somebody that said nitrogen and oxygen gas. They are not greenhouse gases. They do not trap infrared. In fact, nitrogen gas and oxygen gas, like I said, if we didn't have the magnetosphere, they go away. We wouldn't have them in the atmosphere. And if it wasn't for plants constantly pumping oxygen out and bacteria constantly pumping nitrogen out into our atmosphere, we wouldn't have those. And those two are the bulk of what does make up the atmosphere on this planet. I'll show you guys a chart. Probably should have thrown it in Canvas, but I didn't do it. Okay, there's 4 major greenhouse gases. There's other things like the fluorocarbons, but the 4 major gases, the 2 that are going to be mentioned more than anything else. Number 1 is going to be carbon dioxide because of the burning of fossil fuels. The fact that we are pumping a heck of a lot of that stuff into the atmosphere that normally wouldn't be there. I know volcanoes do it, but we're doing it on an accelerated rate. Water fluctuates with temperature. Okay, if it's warmer, you have more evaporation, the percentage of water goes up. Water has a high specific heat, it holds on to heat, and it's going to share its heat with the other particles in the air around it. So water is extremely important in regulating the temperature of our planet. So is carbon dioxide. And I probably should have done the carbon dioxide cycle separately from this, but I didn't, and it's too late for me to pull it out. Even if I did pollution first, I'm not doing that. But these 2, they're the ones that really trap and hold on to that reflected infrared, which you think of as heat. The way that like predator sees, and pit vipers, ones with the holes in their mouth, see. The 3 things that make it a Goldilocks zone here is we're the perfect distance from the sun. And we have that albedo effect between snow and then things that are light and things that are dark. And like I said, greenhouse gases aren't necessarily something bad as long as they don't get out of balance. That's the issue. All right, I'm going to try not to get on my soapbox. Most of our atmosphere is made up of nitrogen gas. I've seen 77, I've seen 78%. So the bulk of it's nitrogen gas. The rest of what's left over is primarily oxygen gas. After that's argon gas. You keep getting smaller and smaller and smaller. Carbon dioxide is 0.036% currently of our atmosphere. So there's really not that much present considering how much of an effect it has with trapping heat. Like I said, water is controlled primarily at the temperature of the surface of the earth. The warmer it gets, the more vapor goes in the air. The colder it gets, the less vapor goes into the air. And like I said, we're perfect. It allows water to stay in its 3 main states. So we've got obviously ice at the poles. We've obviously got water just about everywhere else, but we also have the vapor, the gaseous state. I can't remember if I put another one on here or not. I did not. Well, at least I did not with my original one I printed off. No. In the gaseous state, the water vapor, the moisture in the air, like I said, that's what really controls the temperature of the planet. That's why on the coast, you don't have a huge temperature swing between night and day, but in the desert, it can be a difference of 60 to 80 degrees overnight. They hold on to infrared light. That is what IR stands for. Your 4 important greenhouse gases, and yes, there are others besides this. I just didn't have enough time to do every single thing that gets pumped, bless you, that gets pumped into our atmosphere. So these are the 4 that we're going to focus on today. As I said, there are the fluorocarbons, the CFCs, with coolants and refrigerants. To learn that the old type of Freon, which I can't remember the name off the top of my head, We don't use that anymore because it was putting those aerosols into the atmosphere. That was when it was like, oh, there's a hole in the ozone and all of our skin is going to melt off and we're all going to die and the plants are all going to burn. And it didn't happen. But a big reason why that stopped was because we stopped using those nasty aerosols. I can't remember all the names, but these are the ones we're going to focus on. This is the most abundant. This is the most powerful. This is the one that we're producing like crazy. This is a side effect of pollution, which we're going to get into pollution a little bit more tomorrow. Well, that is the paper tomorrow. So the most abundant greenhouse gas is water. And it's going to help control the temperature of our planet. Now, so does carbon dioxide. Like I said, we're going to get into the not the carbon cycle, the carbon dioxide cycle, which goes between air and goes between liquid and goes between solid, depending on how it's been absorbed. Once again, IR is short for infrared. So water, high specific heat, takes a lot of energy to heat it up. It absorbs this infrared energy, this heat. And as the vapor is moving around, it carries the heat with it. This is the whole reason why we sweat, is to cool us off. Water evaporates, the sweat evaporates, and it takes the heat with it. And if it's your sweat, now it's floating around in the air, and it's giving your heat that it took from your body to the other things around it, the things like the nitrogen gas, the carbon dioxide gas, the oxygen gas, all the other air particles that are in the air that we breathe. But we've mentioned this, we're going back to space. Water is brought to us by comets at the formation of the Earth. So we're between 4 and 4.6, 4.57 billion years ago. It wasn't in the liquid state until later. It was trapped inside the molten Earth. And we had the crust form. You go way back to the first 6 weeks. The global differential, the chemical differential, where the heavy things went to the core and the lighter things went to the surface, and we started to form a crust. And then along came the volcanoes, and they all spewed these gases out into the atmosphere, and that's where our water came from. The volcanoes belched it out for us from the interior of the Earth. So we've had water on this planet for a very, very, very long time. It's the life on the planet that didn't start until about 2.5 billion years ago, because the volcanoes had to do their thing first. Volcanoes are very important to the health and to the life of this planet. And they can turn around and kill us pretty quickly. We've got a major eruption going on. I should take attendance. See Joseph, Sarah. If you guys are online and I'm mentioning you, I'm going to check in just a second. Let's get the next one. I'm going to double check. There's not that much on the next one. The next slide is the chart that I probably should have thrown into your Canvas, but I just didn't do it because we've already covered the atmosphere and what makes up our atmosphere in like the second or third 6 weeks. But this just sort of shows you our particular planet, and it shows a couple of the others. I think next year when I do space, I'm going to go back and do my alien project. You actually take a look at the chemical composition of the individual planets, both atmosphere and surface, and you get to create life. And like I said, sometimes I've seen this as 78, and sometimes I've seen it as 77, but I pulled the information off of this chart specifically. And I don't see the year that was on it. Obviously, things do fluctuate just a little bit when you go down to like the hundredths with percentages. Right, carbon dioxide comes from volcanoes going boom, okay, belching those gases into the atmosphere. Burning of things like fossil fuels and wood releases, because in the opposite of photosynthesis, water and carbon dioxide are produced. If you just sort of flip this thing around. And then the things that are breathing that aren't plants. I don't know of a single plant that breathes out carbon dioxide. I think they're all photosynthetic, I believe. All right, so carbon dioxide can be stored in what is called a sink, not like this, not this. It's a holding body. And so It can be in the form of carbonic acid in the ocean. Okay? It can make limestone, these specific types of rock, different types of carbonates. I didn't put their formula on here. The stuff that's not put into rocks or put into liquid form is going to stay in the gaseous form. I just didn't put the chemical formula for calcium carbonate. We got CaCO3. That's primarily limestone. I don't know what sandstone's differential is. I think it's also a calcium carbonate. But most of the carbon dioxide is actually trapped in rock in the form of what is called a carbonate. Not carbonated like a drink. Although that's what causes the bubbles, is the carbonic acid that's in it. And when you open your soda, that's the carbon dioxide that's bubbling out. If I open my coffee. And like I said, I probably could have done the carbon dioxide cycle separately. I just sort of smooshed it in with this. Because we are running out of time. Stopping what we're doing next week. When it rains, we have weathering of rocks. And as the rocks are broken down, it actually helps pull carbon dioxide out of the air. And then that stuff is being carried, the dissolved minerals, the carbonates, the things are carried with the water, eventually end up at base level, which the ultimate goal for water is the ocean. And in the ocean, these minerals will interact with carbon dioxide that has been pulled out of the atmosphere and make specifically limestone. Okay, our country, the bulk of the plain area is limestone because it was originally covered by shallow sea. Not all bedrock of continents is limestone. A lot of it's granite, and we do have some granite. It's just mostly limestone because the vast majority of our country was submerged. And so once you have limestone, then we have plate tectonics going on, where the ocean floor is more dense and it's going underneath. Limestone's made in the ocean. It's going underneath the continental shelf. And as it's being pushed down to the mantle, eventually it gets remolten. And then you're going to have, I thought there was one more. Then you're going to have volcanoes that take this molten material eventually and spew it back out. And then the carbon dioxide gets back into the atmosphere. That is the basis of the carbon dioxide cycle. It's affected by temperature big time. The amount of carbon dioxide in the air basically determines if we're going to be going into an ice age or if we're going to be going into a warm phase. And it's basically the thermostat for our planet. There's other things, but carbon dioxide, how warm it is, determines how much carbon dioxide gets pulled into the ocean, determines how much carbon dioxide gets trapped as limestone. If it gets trapped, then the carbon dioxide goes down, temperature goes down, it gets sucked into the volcanic activity. You're probably at an ice age at this point. Volcanoes go boom, pop their top, carbon dioxide comes up and it starts warming it back up and we remelt. It's the basis of the cyclical pattern of ice ages. It just takes a long time to be able to do all of this. So this is a continuation of the previous one. They get pulled down into the mantle. The carbonate gets melted. And you've got the CO3 becomes CO2 and it gets into the gaseous state and out it comes from the volcano itself. Oops. But this particular greenhouse gas is not the only one, but the most important gas as far as controlling the cyclical temperature. It fixes it. If it's too hot, certain things happen. It'll cool everything back off. If it's too cold, certain things will happen. Given enough time, volcanoes do their thing and it'll warm it back up. which is the next two slides. It looks like I said, this was printed off before I started shortening down and adjusting the notes because I realized it was just too much. So weird. So weird. So we are in a warming trend. Okay, we've been in a warming trend since like the mid-60s, according to all the different data that we have, both the atmosphere and the ocean, both of them. And we've already mentioned what the direct side effects of said warming trend are. But when the Earth warms, and it does not need to be like 1,000 degrees kind of warm, the carbon dioxide gets absorbed by the ocean quicker. Okay, and like I said, I don't know how much chemistry y'all remember. When you increase the temperature, like when a reaction's going on, the reaction is gonna keep going faster. It's just more heat, more energy, particles are colliding into each other faster, make products faster. I'm actually learning this in my chemistry class right now, the activated complex with a hump that happens before the reactants actually become products. But when you do increase the temperature, you have more of an interaction between the carbon dioxide and the surface of the ocean, in the atmosphere and the hydrosphere, and it increases the rate at which that carbon dioxide is absorbed into the sink that is the ocean, making these carbonates, making limestone, pulls carbon dioxide out of the atmosphere, which is going to end up cooling the planet and possibly triggering an ice age. Now, I'm not saying that we're going to have an ice age tomorrow, but warmer temperatures, when you follow through the cycle of the carbon dioxide cycle, actually trigger a cooling off of the planet. It's the way it works. Now, we have other things that are going on right now, which are actually driving the temperature warmer and warmer and warmer. No, I do not know the temperature that's the tipping point that actually starts cooling it back off. I didn't look at any of that. There are many different cycles that are going on simultaneously that are affecting the temperature of our planet. And we are messing everything up because the Earth is really, really, really good at fixing things when they get out of whack. She can just forget, she, he, it, whatever the Earth is left alone to do what it does, that it's been doing now for billions of years. Now, if we start to cool, then your absorption of carbon dioxide into the water is going to be slower. Your volcanoes are still going to do what volcanoes do, and they're going to belch these gases out, all of them, including carbon dioxide. And the volcanoes are responsible for helping us to get out of ice ages. Increased carbon dioxide, because of the volcanoes, would increase the temperature of the planet, and potentially, if we are in an ice age, that's something like this, get us out of an ice age. Actually, really good on here. I was worried. Yeah, it should be open up here. What's something else can happen? No, no, we're not done. We're just getting through this a heck of a lot faster than I thought we were going to. All right, positive and negative feedback. Okay, these are your cycle loops. Okay, so in positive feedback, they accelerate whatever trend is happening. So positive, I know you think positive is, it's good, it's positive. Positive feedback loops make your problem worse. They continue the trend. With carbon dioxide, the carbon dioxide cycle is a lot more complex. I really should have split this off. Now, note for next year to do that. In a positive feedback, the mechanism, whatever mechanism it is, okay, if it's positive, then an increase in carbon dioxide is going to beget or cause an increase in more carbon dioxide to be produced. It makes it worse. In a negative feedback, okay, this is what the planet likes to do. If you would increase the carbon dioxide, it absorbs into the ocean, gets pulled out, cools it off. Negative feedback causes the opposite. It's a correcting, it's a self-fixing mechanism. And our natural carbon dioxide cycle does this. It's been doing this for forever. It just takes time. Like I said, the evil bad humans with our use of fossil fuels for production and for heating and for industry and for farming and for all the other things that we need, because, you know, we don't want to die. We want to be comfortable. We're throwing this out of whack. And the Earth's natural ability to use its negative feed, the carbon dioxide cycle, this one, that the Earth wants to do, the Earth is trying to do, we're just messing it up. But eventually the Earth is going to try to suck enough carbon dioxide out of the atmosphere. It's going to poison all the fish. It's going to turn the oceans acidic. This has happened repeatedly with mass extinctions, but they've been volcanic triggered. They haven't been people triggered. It's just, and it's like, ooh, I don't want acid rain. I don't want the oceans to turn acidic. I don't want to not have any more fish. But that's the natural process that the Earth has to use to be able to fix it. Because eventually, that carbonic acid is going to precipitate into limestone, and it's going to pull the acid back out of the ocean. I don't have the slightest idea how acidic the ocean became in the Permian extinction that almost wiped out everything. And then you fast forward to the one that took out the dinosaurs. I don't know how acidic it made the ocean there either. But those two extinct, well, the Permian extinction was the worst of the worst. And we've had so many, and that's something else that we've already done. We've already done extinction events. All right. Plants are absolutely necessary, duh. Okay, they're the most common form of life. Okay? I mean, all plants, grass, trees, lichens, mosses, clovers, flowers, everything, all trees. And if it was not for their photosynthetic ability, okay, that mutation that happened about 2.5 billion years ago with an ice age that triggered that one, without their ability to constantly replenish oxygen gas in the atmosphere, it would be stripped away. Oxygen is not naturally something that was on this planet in its gaseous state until this genetic mutation occurred with the photosynthetic bacteria about 2.5 billion years ago, with the Huronean ice age, the big ice age that happened that triggered that mutation. But the photosynthesis is going to take your carbon dioxide, okay, from the atmosphere. I just erase the biochemical pathway, but I don't care. It's going to pump out oxygen. Woo, great for us. In the process, it takes the carbon from the carbon dioxide and starts making sugars. And we come along and eat said plants and take said sugars and make things like proteins, and it's used in all types of nucleic acid, DNA and RNA. But the nucleic acid takes the nitrogen out of the atmosphere too. Do I have another one? No. But naturally, without this biochemical pathway, we would not have oxygen in its gaseous state. We have nitrogen in its gaseous state as long as there was bacteria, because with the nitrogen cycle that we talked about last week, yes, the bacteria is what pumps nitrogen gas out. You have genetic mutation photosynthesis, that bacteria started pumping oxygen out. Volcanoes are pumping carbon dioxide out. They're pumping water out. It's just sort of interesting how everything happens just perfectly on the planet. Oxygen is unbelievably reactive. It likes to buddy up with everything. It likes to make rust, iron 3 oxide. It likes to tarnish silver. It likes to react with metals. It likes to react with copper to make pennies turn that greenish color, like the Statue of Liberty. It's oxidation. Oxygen is extremely reactive, so it does actually not want to stay in its gaseous form. Thankfully, the plants turn it back that way. I could show you guys redox reactions too if I wanted to. There's so much chemistry in this unit. You guys just unfortunately had COVID last year when you were doing chemistry, so I don't know how much of it you got. I don't even know if you guys did redox reactions. We didn't do redox reactions this year. Skip. Oh, itchy eyes. Oxygen in the form of ozone, which is O3. Okay, it's a mutated type. Whoops, there's one more. Ozone actually absorbs ultraviolet light, okay, and it protects us. Some of it gets through, or you wouldn't be like me and you're outside for 15 minutes and you're constantly pink. Like, I swear, I'm constantly red because I burn. So oxygen provides life, okay, provides oxygen for us to breathe, or plants provide oxygen for us to breathe. It protects us from ultraviolet radiation, because if you have too much UV exposure, it'll cause cancer. Everything causes cancer. What am I saying? Too much anything causes cancer. Too much water will kill you. Too high an oxygen concentration will kill you. But yeah, oxygen doesn't like to be in its O2 form. Thankfully, the plants fix that for us. All right, magnetic field. We talked about this too. Something I needed to probably go into way more depth when we were doing this a while ago, how the magnetosphere truly functions. I didn't think about it when I was building the notes at the time. I said this class will change drastically from year to year. So I'm realizing that things are either in the wrong spot, or I should have included something or excluded something. So more chemistry. One more on here. The magnetosphere is a protective bubble. Okay, it's caused by the friction of the liquid outer core around the solid inner core. It's like taking a balloon and rubbing it on your head and making a static electricity. You can actually feel the bubble around the balloon if it's got enough of a charge. Obviously, this is not a balloon being rubbed on your head, but that friction between the two cores causes us to have a north and a south pole, causes us to have this magnetic protective bubble that if we did not have, the solar radiation would be able to penetrate into our atmosphere, and the radiation from the sun would take these three gases and would strip them apart. And then in the state that they turn into, which is not normally the way that these gases are. Normally, hydrogen is H2, oxygen is O2, nitrogen is N2. That's normal, but that's because of the magnetic field. Without that, these things become so light that they're light enough to escape to escape the gravitational pull of our planet. We wouldn't have them. This is basically what's happened to Mars. Its core is not, I mean, if it's functioning, it's barely functioning, because Mars does have a very, very minute atmosphere. It's there. It's just not thick enough. I don't know if we're going to actually be able to terraform it. It's not thick enough to let life happen the way it does here. When it used to, we have found fossilized bacteria on Mars. We know that it used to have liquid water. I showed you the river channels in the notes a couple weeks ago. But yeah, this solar wind, that wonderful hydrogen bomb that you can't see right now because of the clouds, it's pretty gosh darn deadly. It is a nuclear bomb. And when it sends its solar wind to us, that's what interferes with these puppies. I'm not sure if we're getting ready to go to another solar maximum, but when we do, expect it to jack with this. And there's nothing that the cell phone companies can do. It interferes with our telecommunication devices, satellites, the things that are up in space. We know we've had multiple ice ages. I am not going to go in depth with this. We had the big one that happened, the one where the planet was essentially frozen solid, that triggered exoskeletons with the Precambrian. When you're frozen, okay, the carbon dioxide can't get into the water. It can't get through the ice. And so the ocean doesn't have the ability to be a sink, to pull the carbon dioxide out, turn it into carbonic acid, turn that into limestone, and it stops the carbon dioxide cycle. So carbon dioxide, volcanoes are still going bleh. Okay, so they're still spitting carbon dioxide out, but it doesn't have the ability to get through the ice. And that's what triggers the temperatures to go back up. And that's the negative part of the feedback, which is good. It's what melts the ice and lets things go back for what we consider normal. Earth doesn't care. Earth's cyclical. There's one more on here. So everything on this planet is cyclical. Every single thing. And there are things that this planet can do that we are not able to stop. Primarily, we have like Yellowstone blow up. We are in such doo-doo if Yellowstone goes boom. Carbon dioxide is a necessary greenhouse gas. I'm not saying pollute. Don't misconstrue what I'm saying, but it's necessary. If it's not in the atmosphere, then we ice age. It's what happens. So, I don't know. We were supposed to be in an ice age in my lifetime. So said Al Gore, and then he switched his mind, and he said that New York was going to be completely submerged underwater by like 2005, and yeah, that didn't happen. And the acid rain was going to melt all our faces off. And, I mean, rain's already acidic. Stupid. It's just acid rain is way more acidic. All right, let me double check my attendance one more time online. If you did not do the thing, it has to be loaded by now. Oh, my computer's dying. Okay, so unless you did your fossil fuels within the last 30 minutes, I am missing both the opener and, oh, let me pause I don't like saying y'all's names on the recording.